Okay, so today we're going to start polynomial rings, right? Today I'm going to start polynomial rings. So far in the previous classes we have finished ideals and then subrings, etc., etc. So please go through previous classes. So now we will introduce polynomial rings. It's a very important concepts in UPSC point of view. So polynomial rings, right? Yes. So actually, you know what's in a polynomial. So first you will define what's in a polynomial ring. Let R be an arbitrary ring. So definition. So let R be an arbitrary ring. Right. So this R can be any ring. It can be integers. It can be real numbers. It can be any ring. Whatever you can take. Let R be an arbitrary ring. The set polynomials. The set of all polynomials, the set of all polynomials f of x, that is a0 plus a1x plus a2x square up to an x power n, right? So up to an x power n. Actually it's a polynomial, it can go on up to n. It can be a different polynomial. So a0 plus a1x plus a2x square plus a3x cube and so on dot dot dot. This I can write this as summation n is equal to 0 to infinity a n x power n, right? So these ans that is a1, a2, these are all constants, right? So these are belongs to a ring that we are choosing, right? So this will form a ring. This will form a ring. So let R be an arbitrary ring. The set of all polynomials, that is a0 plus a1x and so on, and these constants are from the ring. Suppose if you are taking R to be an integers, this a0, a1, a3 can be integers. If you are taking R to be a real number, it is a ring. So this can be a real number. So whatever ring you are choosing, you can take the constants from the ring R. This will be a ring, right? This will be a ring. Now a set of all polynomials over a ring. So this will be a ring. Now we will prove that this forms a ring, right? This will forms a ring. So this is denoted by Rx. This is denoted by R of x. So R of x means a polynomial ring over x, and this R is any ring. This R is any ring, and x is the indeterminate. X is the indeterminate. So this is a notation for polynomial ring. So here the R is any ring. It is not a real number that we are denoting. So I will always use real number like this, right? So here this is nothing a ring over x. So this ring plays an important role here. That is, we are choosing the constants to be in the ring. Now we will prove that this is a ring, right? So in order to prove this is a ring, we need to show that we need to show the all the conditions for ring. So actually we can easily prove the set of all polynomials over R is a ring. Now we will prove that ring of we will prove that that is a ring, right? That is a ring. So theorem: the ring Rx, R is any ring where R is any arbitrary ring, then Rx is a ring. We will prove that it is a ring, right? The ring R of x as arbitrary polynomial is a ring. So first we need to prove that set of all polynomials over R is a ring. So for that we need to prove that set R of x with respect to plus is an abelian group, and the ring R of x with respect to dot is closed and associative, closed and associative, and the set R of x with respect to and then satisfy distributive property. This is the one we need to prove for ring, right? Distributive property. So we need to prove these three things. Now, what is R of x? What is R of x? Actually, very easy. You can easily prove. What is R of x? It is nothing but summation n is equal to 0 to infinity a(n) x power n, that is a0 plus a1 x plus a2 x square up to it so on, because it is an infinite ring. So infinite polynomial. Now we will prove that this is a ring. So first we will prove that it is an abelian group with respect to addition. Now if you take two polynomials, remember this R is a ring, right? R is a ring, and we are keeping the ring over polynomials. Now first closed. Now first we will prove with respect to addition. It is closed, right? Because you just take a polynomial. Let us take f of x to be a0 plus a1x plus a2 x square and so on. Let us take g of x to be b0 plus b1x plus b2 x square dot dot dot, and these ai's and b's belongs to the ring that we are choosing. Now what about f of x plus g of x? So it is nothing but a0 plus b0 plus a1 plus b1x plus a2 plus b2 x square and so on. This also belongs to R of x, because here a0 and b0 in R, and R is already a ring. So a0 plus b0 will be in R again. Again a1 and b1 are in R, and since R is a ring, it is closed under addition. Therefore all these elements are in R, and therefore we have x over every element. So therefore it belongs to R of x. So therefore it is closed. And similarly you can prove associative, right? So f of x, you just take h of x to be c0 plus c1x plus c2x square, and then you verify f of x plus f of x plus g of x plus h of x is same as f of x plus g of x plus h of x. You can easily verify. And what about identity? What about identity with respect to addition? Identity. So identity is you need to take one polynomial. Let us take that polynomial to be a0 plus a1x plus a2x square dot dot dot. You have to add some other polynomial. You have to get that same polynomial again. So a0 plus a1x plus a2x square and so on. So what is this polynomial? This polynomial is nothing a 0 polynomial. So 0 plus 0x plus 0x square and so on. So 0 polynomial is the additive identity. And what about inverse? So for polynomial a0 plus a1x dot 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 a2 dot dot dot, the inverse will be minus a0 minus a1x minus a2x square dot dot dot. This will give you 0, because these two will get cancelled. So negative of the polynomial is the inverse with respect to addition. Negative of the polynomial is an inverse with respect to addition, right? Yes. So therefore we have proved, and also it is abelian also. It also abelian also, because f of x plus g of x is same as g of x plus f of x. If you take f of x to be some polynomial, g of x to be some polynomial, then whatever add, you just add f plus g or g plus f, it is both same. So far we have proved with respect to addition it is an abelian group. With respect to addition is an abelian group. Now we will show that with respect to multiplication, it must be closed, right? It must be closed. Again you just take f of x to be a0 plus a1x a2x square dot 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 dot, and then you take another polynomial g of x to be b0 plus b1x plus b2x square dot dot dot. Now what about f of x into g of x? It is nothing but a0 plus a1x dot dot dot, and then b0 plus b1x dot dot dot. If you multiply, you will get another polynomial, and this polynomial will be in R of x again, right? So therefore it must be closed, and also it is associative with respect to multiplication. Now therefore we have proved this thing and this thing. Now we need to prove it is distributive, and again it is distributive because f of x into g of x plus h of x is same as f of x g of x plus f of x h of x, right? This is also true for a polynomial. You just take f of x to be a0 plus a1x plus a2x square dot dot dot, and then take g of x to be equal to b0 plus b1x plus b2x square dot dot dot, and then you take h of x to be c0 plus c1x plus c2x square dot dot dot, and then you prove these are equal, right? So elementary form. So therefore we have proved the ring Rx. Rx is a ring, right? The set of all polynomials over a ring R is a ring. The set of all polynomials over an arbitrary ring R is a ring. Now we will prove second theorem. The first theorem is we have proved that set of all polynomials is a ring, right? Set of all polynomials is a ring over an arbitrary ring R. Now we will prove that theorem 2, if R is any arbitrary ring, if R is any arbitrary ring, if R is any arbitrary ring, if R is any arbitrary ring and R dash is set of all constant polynomials in Rx, and R dash is the set of constant polynomials, set of constant polynomials in Rx, then it's natural, right? Then R dash is isomorphic to R. So what they are doing is, so we'll prove what they are saying. So if R is any ring, and R dash is set of all constant polynomials in R of x. So what is R of x? R of x is nothing but a0 plus a1x plus a2x square and so on, and these ai's are in R. Now what this a0 is the constant polynomial, right? So we are going to call this as R dash, and R dash is set of all constant polynomials, and this a0 can be an element in R because the entries a0, a1, a2 are belongs to R. So a0 can be in R. Now if you vary a0, you will get the entire ring R. It's obvious, right? So R dash is there. We are taking only the constant polynomial, and if you vary, this element can be an any element of ring R. So this is equal to R. This is equal to R. If you vary a0 to be in R, for example, if you take the ring to be equal to integer, you just take z, R is equal to z, right? Then this will be a0, and this a0 belongs to integer. So this set is nothing but 0. It can be plus or minus 1, it can be plus or minus 2, it can be plus or minus 3, which is isomorphic to z, right? Set of all constant polynomials in R of x, then R is isomorphic to R. R is the ring that we are choosing, right? It's a very natural result. So what we need to show is, so whatever ring we are choosing, here we are varying these coefficients to be in the ring R, and if you take only the constant polynomial and if you vary the ring, if you vary this element to be in R, then you will get the entire R. So therefore these two are isomorphic. So R dash is the constant polynomials. So constant polynomials. So constant polynomial R dash, which is nothing but a0, and this a0 can be an any element in R. It can vary over R. We need to prove, what we need to prove, what the ring that we are choosing is isomorphic to R dash. The ring that we are choosing is isomorphic to R dash. So therefore we need to create a map. From R to R dash, and then need to prove that map is 1 1 onto 1 homomorphism. So I'm going to create a map F from R to R dash. So R dash is the set of all constant polynomials, and R is the ring that we are choosing. So I'm going to denote like, so whatever okay, so whatever element you take, and this will move to a into x power 0, that's it. Because here we have R dash constant polynomial, right? That is this is nothing but x power 0. X power 0 is nothing but 1. This is the map I'm defining. This is nothing but a, right? This is nothing but a because x power 0 is 1. So I'm writing x power 0 because I'm to make sure that this element belongs to polynomial ring over R, right? So I'm denoting a map like f of a is equal to a x power 0, which is nothing but a. So we will this is a map. So from R to R is a map which is nothing but a. Now actually this is an identity map, right? This is identity map. So whatever element you are choosing, that is moving to itself. So it is an identity map. So first we will prove that f is 1 1. Clearly it is 1 1, right? So f of a is equal to f of b. So this is nothing but a x power 0. This is nothing but b x power 0. This implies a is equal to b. And f is onto. So clearly you can verify. So for every element for every y in R dash, there exists some a in R such that this y can be written as f of a, right? So this onto, and we need to prove that f is homomorphism. That means we need to prove f of x plus y is equal to f of x plus f of y and f of xy. So since it is a ring homomorphism, we need to prove that, remember these two are ring homomorphisms. We need to prove two conditions: f of x plus y is equal to f of x plus f of y, and f of xy is equal to f of x into f of y. So what about f of x plus y? So this is nothing but f of a. So okay, we will write a plus b. So f of a plus b. So this is nothing but a plus b x naught. This is nothing but a x naught plus b x naught, and this is nothing but f of a. This is nothing but f of b. This is f of a plus b. And again, what about f of ab? So it is nothing but ab x power 0. So this is nothing but a x power 0, b x power 0. This is nothing but f of a into f of b. So therefore, these two are isomorphic. That is, set of all if R is any arbitrary ring and R dash is set of all constant polynomials, then in R of x, then R dash is isomorphic to R. Right? Yes. Now we move on to theorem 3. So theorem 3 is very important. So what we have seen so far is, if R is a ring, if R is any ring, then R of x is also a ring. This is what we have seen, right? R of x is also a ring. If R is any ring, then set of all polynomials over R. Over means the coefficients are in R, right? So over means R of x over ring R. We need to pronounce like R of x over a ring R. And over a ring R means that a naught, that is that a naught, a1, a2, that coefficients can be in the ring R. That is the one we are telling like over R. Over R means the constants, the coefficients of the x square R belongs to the ring R. Now if R, so far if R is a ring, then the polynomial over it is a ring, that is R of x a ring. Now theorem 3 is, if D is an integral domain, then D of x, that is a polynomial over integral domain. Theorem 1 is polynomial over ring is a ring. Here what we are proving is polynomial over integral domain is also an integral domain. If D is an integral domain, then D of x, that is polynomial over integral domain. In the previous theorem, polynomial over ring is a ring. Polynomial over integral domain is a integral domain. So whatever integral domain you choose, and you just form a polynomial ring, that is the coefficients you are taking from D, that is also an integral domain. This is the one we need to prove. So we will prove on proof. So proof, let D be a commutative ring with 0 divisors with unity element. So I am assuming that D is an integral domain. Assume D is integral domain. So what is integral domain? it's a commutative ring without 0 devices. That is commutative, that is commutative ring without 0 devices. Without 0 devices. And also with unit element 1. It also has unit element 1. So it is a commutative, D is a commutative ring without 0 devices and also has a unit element 1 by definition, right? Yes. Now so we are assuming that D is integral domain, right? So D is integral domain. This implies D is a ring, right or wrong? D is a ring. So if it is an integral domain, obviously it is ring, right? Every integral domain is a ring, right? So therefore D of x will be a ring. D of x is a ring by theorem 1, because theorem 1, if R is any ring, then R of x is also a ring. So if D is ring, then the D of x is also a ring. But what do we need to prove? D of x is an integral domain. D of x is an integral domain. Now we will need to prove that polynomials over x, the coefficients are from integral domain is a yes. Now we need to prove D of x is integral domain. That means we need to prove D of x is commutative. It is because integral domain is commutative without 0 devices and it should have unit element. So 3 conditions we need to prove for integral domain. So D of x is commutative. We need to prove that D of x is commutative, and then need to prove D of x is without 0 devices, and then we need to prove D of x as unit element, that is this as an element 1 in it. So if D of x satisfies these 3 conditions, then it will be a integral domain. It will be an integral domain. So obviously it is ring. So ring which is commutative without 0 devices and as unit element will be a integral domain. So now we will prove one by one. So first we will prove that D of x is commutative. D of x is commutative. So let us take 2 polynomial, and actually it is very easy task, right? So let us take 2 polynomial f of x into g of x. Let us take f of x to be equal to a naught plus a1x dot dot dot. Then you take b naught plus b1x dot dot dot, and these ai's and b's are in D, because the D is the integral domain, and this I varies from 0 to etc. So these are, so what about f of x into g of x? F of x into g of x. So naturally f of x into g of x is same as g of x into f of x. You can just take any 2 polynomial, you can just verify. So therefore d of x is commutative. D of x is commutative. Now we need to prove that g of x now we will prove that the third condition, that is d of x as unit element. So clearly the polynomial 1 plus 0x plus 0x square dot 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 will be in R of x, which serves as a unit element in g of x, because 1 must be in ring R. So clearly here also the constant polynomial with 1 plus 0x plus 0x square will be in R of x, which is serves as unit element. Unit element of Rx side dx. Unit element of dx. Now we need to prove the second condition, which is d of x is without 0 devices. D of x is without 0 devices. So that means the product of 2 polynomial is 0 if and only if one of them is 0. Again, it's very natural, right? If you multiply 2 polynomials, if you get an answer to be 0, then one of the polynomial has to be 0. So we have assumed that D is an integral domain. Actually, you can write that in theory. So let f of x and g of x be two non-zero elements in d of x. So I am taking two non-zero polynomials in d of x, then f of x into g of x cannot be equal to 0, because natural, right? If we take two polynomial which is non-zero polynomial, if you are multiplying, it cannot be equal to 0, because you have to be very intuitive, right? So if you are multiplying two polynomial, what we are doing is we are just multiplying the constants, the coefficients, right? We are multiplying two polynomial, for example 2 plus 3x into 3 plus 4x square. If you are multiplying, what we are doing is we are just multiplying the coefficients, right? It cannot be the coefficients, since the coefficients here are in D, right? The coefficients are in D. D is integral domain. D is integral domain. By assumption, D is integral domain. Therefore, when multiplying coefficient, two non-zero coefficient, it cannot be equal to 0, because we assume that D is integral domain. Therefore, the coefficients are in D, and since D is integral domain, this will never be 0. That is, f of x into g of x can never be equal to 0. That means it has no zero divisors. That's it, right? So therefore, we have proved all three conditions for. So the first theorem what we have proved is, if R is any ring, then polynomial over ring is a ring. Next, polynomial over integral domain is again an integral domain. And then we have proved the set of all constant polynomial is isomorphic to the ring R that we are choosing. Now we will prove that if f is a field. Now first we have started with, if R is a ring, then the polynomial over R is a ring. If D is an integral domain, then polynomial over D is also an integral domain. Now we are going to prove, if f is a field, then polynomial over f is also not a field, right? Not a field. So if it is a ring, then R of x will be a ring. If it is integral domain, R of D of x will be integral domain. But if it is a field, then the polynomial ring over field is not again a field. That we will prove now. So rather, first we will prove the theorem 4. So theorem 4 is, if f is any field, actually this follows from the previous theorem. So if theorem 4, if f is a field, in the set, then the set Rx, right, and the set Fx is integral domain. It will be an integral domain alone, it will not be a field, right? If f is a field, that is coefficients are here from field. The coefficients are here from field. So this will be an integral domain alone. So you can just verify 2-line proof for that. It naturally follows from previous theorems. Now we will prove the important theorem. This take this exercise. So theorem 5. So what theorem 5 is? A polynomial domain Fx over a field F is not a field. This is very important, right? So if it is over R, it is ring. If it is over integral domain, it is integral domain. But if it is over a field, it is not a field. That is, a polynomial ring is not a field. Okay. Now, what we need to show, f of x is not a field. F of x is not a field. That means we need to prove that non-zero polynomial has no multiplicative inverse. This is by definition. That is, you need to prove that non-zero polynomials has no multiplicative inverse. Non-zero polynomial has no multiplicative inverse. Let us take an element f of x in fx. Right? We are choosing a polynomial in fx, that is set of all polynomials with coefficients are from the field, right? Yes. Such that we are choosing a polynomial whose degree is strictly greater than 0. We are taking some polynomials whose degree is greater than 0. That is, we are not taking constant polynomial. That's it. So whatever you just take a polynomial in f of x, which is not constant polynomial, because constant polynomial is degree 0. So we just take some other polynomial in fx. Now what about inverse of f of x? What about inverse of f of x? The inverse of f of x. The inverse of f of x cannot be zero polynomial. Actually, we can go by intuition. So what will be the inverse of f of x? So f of x into something, you need to get 1. That is, you need to get 1 plus 0x plus 0x square and so on. So what this polynomial will be? What this polynomial will be? For example, if I take f of x is equal to 3x plus 2. If I take f of x to be equal to 3x plus 2, then what? So that is 3x plus 2 into something, you have to get 1. So what this polynomial will be? So actually this polynomial has to be 1 by 3x plus 2, but this is not a polynomial. This is not a polynomial. Why? Because polynomial means f of x is equal to a0 plus a1x plus a2x square and so on. Remember, the x must be positive. All the x must be, here it is x power 0, it is x power 1. Polynomial means x should be 0, 1, 2, 3. That is, powers of x should be 0, 1, 2, 3. But here, what is the power of x? This is not a polynomial, because this is not, if you take above, it will be minus 1, power will be minus 1. Therefore, this is not a polynomial. So you just have to give a counter example. So for that, what we will do is, let us take f of x to be equal to x. Just for simplicity, we will take f of x to be equal to x. Now what about inverse of f of x? So f of x into something, I have to get me 1. That is 1 plus 0x plus 0x square etc. Because unit element of the multiplicative entity for d of x is 1 plus 0x. Now this polynomial has to be here we are choosing supposed to be x. So x into something have to be 1. So this has to be 1 by x. But this does not belongs to the field x. That is, this is not a polynomial. 1 by x is not polynomial. Because this is nothing but x power minus 1. X power minus 1 is not a polynomial, right? Therefore, the multiplicative inverse does not exist. That means it is not a field. So if R is ring, then R of x is a ring. If D is integral domain, then D of x is an integral domain. If F is a field, then Fx is not a field. This is the conclusion we are doing. now we will have to prove that division algorithm. So after proving division algorithm, we will prove principal ideal ring. Okay, now we need to prove division algorithm, principal ideal ring, and then unique fraction theorem for polynomials. Okay, so next class we will continue. We need to prove that we are only left with few topics in polynomial thing. That is, we need to prove that it satisfies division algorithm. Division algorithm we need to prove, and then Euclid's division lemma, and then there are some 2 or 3 theorems in polynomial rings. Right. So we'll see in the next video.